Okay, so we're starting on Unit 3, which is really the important unit of this course, which is our dosage calculations. And what we're going to look at today is we're going to start out by talking about dilutions. Now, to talk about dilutions, we need to first talk a little bit about solutions. We talked about these a little bit in Unit 2 when we were looking at mixing solutions and getting a desired percent from the percents we have. But again, what we're looking at today is we're just looking at diluting a solution, a special process called a dilution. So when we perform a dilution, we're taking an existing solution or just an existing medication, and we're diluting it with some sort of a non-medical substance, a neutral solution we call it, which would be saline or sterile water or something like that. So what we're looking at in a dilution is we have two parts. We have either a serum or a concentrate. Serum, of course, is the generic term we use for any sort of medication, whatever it is. So that would be the medication in its pure form. Or a concentrate would be a solution that's already been prepared with that serum that has a higher level of concentration, a higher percentage of the serum in it. And then the second part that's going to be going into that dilution is some sort of a medically neutral substance. And we use that abbreviation NS that could stand for neutral solution or normal saline or just plain sterile water. So, of course, the concentrate itself doesn't have to be a certain percentage. All we know is that after the dilution, the concentration or the percentage of the medication in that solution is going to be lower than when you started. So the term concentrate just means a higher percentage than in the end. So in a dilution, let's say that we are given that we have a 1 in 6 dilution. The 1 in 6 is expressing a ratio. And I'm going to write it as a fraction like this, 1 in 6. The 1 represents the serum or the concentrate. So for dilutions, when I write serum, I'm referring to serum or concentrate. The 6 refers to the total solution, the total final amount of solution. So a 1 in 6 dilution would be 1 part of serum or concentrate in every 6 parts of total solution. So let's say we want to know how much insulin is used to create 480 milliliters of a 1 in 6 dilution of insulin and water. So the 1 in 6 dilution, 1 in 6, the 1 represents the serum, in this case the insulin, and the 6 represents the total solution. So as we look at this, we have to ask ourselves, do we have the number that represents one of those? Well, the number we're asked to find is how much insulin. So that would be the top number that we're asked to find. Do we know the total solution? Well, yeah, create 480 milliliters of that dilution. That would be the total solution. So there's 480 milliliters of total solution. So now that we're only missing one number in our proportion, we can cross multiply and divide. 1 times 480 divided by 6 is going to give us 80. And of course the units on that, since these are ratios, the units on the top number have to be the same as the units on the bottom number. So that'll be 80 milliliters. So it requires 80 milliliters of insulin to create that 480 milliliters of the 1 in 6 dilution. Now there are several other ratios. When we talked about ratios, we talked about the other possible ratios that could be created. So let's look at this 1 in 6 again in our dilution. So the 1 in 6 dilution gave us a ratio of 1 to 6, and the 1, of course, was the serum, and the 6 was the total solution. But what if we wanted a ratio of serum, or concentrate, to our water or neutral solution that was added? Well, that ratio, we would have 1 part of serum still. The parts of water or saline that was added to it would have to be the difference between the serum and the total. Well, if out of 6 total parts, if 1 part is serum, the other 5 parts has to be water, or in this case, saline. So the ratio of serum to saline is 1 to 5. Now with that, it'd be pretty easy then to state what is the ratio of saline to total solution. Well, we've already established that out of that total solution, 5 parts are saline, and the total is still 6 parts. So it would be a 5 to 6 ratio of saline to total solution. With those ratios in mind, let's take a look at some other problem. Let's say how much sterile water is required to create 560 cc's of a 3-in-7 dilution of lidocaine in water. So we have the 3-in-7 dilution. I'll start out with that. Now the 3 represents the serum, the 7 represents total solution. When we look at this, we have the total solution, 560 cc's of that dilution. That would be the total solution. Oops. But do we have the amount of serum? Well, we don't have it, and it's not what we're looking for either. What we're looking for is how much water, or how much normal saline would be used in that. So we don't want the ratio of serum to total. We could find the amount of serum and then subtract if we wanted to. But what we really want is the ratio of water, or NS, to total solution. And it's easy enough to find that ratio. The total solution would still be 7. If 3 out of the 7 parts is serum, 7 minus 3 is 4. There'd be 4 out of the 7 parts has to be the water. And now we can complete the ratio by putting in the 560 cc's. That represents the total. And then cross-multiplying and dividing. 4 times 560 divided by 70 should be 320 cc's of water, of saline. So we can also then look at something like this. How much water needs to be mixed with 240 milliliters of serum to create a 2-in-9 dilution. Okay, so here, 2-in-9 dilution. I'm going to start with that, 2-in-9. And I'm going to label it again. The 2, of course, represents serum, and the 9, as always, is total solution. But here we're not comparing serum to total solution. We do have the amount of serum, 240 milliliters. But we're not looking for the total solution. And again, we could find the total solution and subtract if we wanted to, but we could save ourselves some work by getting straight to the ratio that describes what we need. We could have serum to water. We need to know how much NS. So if we want to make that ratio, the amount of serum is still 2 parts. How much part of water would there be? How many parts of water would there be? There's 9 total parts, and 2 parts are serum. 9 minus 7 leaves us with, 9 minus 2 leaves us with 7 parts of water, or saline in that case. So now to figure out how much saline we need, we know we have 240 milliliters of serum that goes on top. We can now cross multiply and divide. 7 times 240 divided by 2 is what? 840 milliliters of saline. Let's say if we need 720 microliters of (2 and 11) dilution. Of serum NS. How much serum will we need? And how much saline? So now in this case, we could go ahead and we would adjust our ratios, but we really don't have to. This is a 2 and 11 dilution. The 2 represents the serum again, and the 11 again represents total solution. Now in this case, what we are given is the total solution. We need 720 milliliters of that dilution. So we have to stick with a formula that has the total solution in it. Sorry, not milliliters, microliters. 720 microliters of that solution. And since we are creating the solution, we need both the serum and the saline. We just go ahead and use the dilution to find the serum. 2 times 720 divided by 11. It's going to give us kind of an ugly number. Oops, that's not going to work. It's going to give us 130.91 microliters of serum. Now to find the amount of saline, we could just subtract 720 minus 130.91. But I'm going to do this. I'm going to make the ratio of saline to total. And I'm going to use that to check. So the total is still 11 parts. How many parts of saline would there be? Well, if there were 2 parts of serum, 11 minus 2 is 9. And we know, again, 720 microliters of total solution. We cross multiply and divide. 9 times 720 divided by 11 is going to give us 589.09 microliters. Any questions? Okay. Let's take a look at some examples of where this gets used. I mean, it gets used like this to make medications, but it also gets used in testing. Often we'll be doing blood testing, and we have meters that have a certain limit. For example, let's say we have a blood sugar meter. So our blood glucose meter has a limit at 800 milligrams per deciliter. I had mentioned before when we were doing our units of capacity that our deciliters get used for most of our blood tests. That's where the only place that unit gets used. So here's an example of where that's coming up. It's blood glucose is always in milligrams per deciliter. So if our meter is only capable of going up to 800 milligrams per deciliter, but we test a sample of blood and it happens to test above that level. Well, about all we can do, unless we want to get another more expensive meter, is to dilute the blood and do a calculation that way. So let's say we are taking a sample of blood. We have a 20 milliliter sample. And our plan is to use a 1 in 5 dilution in order to complete this test. Most labs have a standard procedure they use, and let's say for this lab, their standard procedure is a 1 in 5 dilution if that blood sample exceeds the capabilities of the meter. So the first thing we need to do is we need to figure out how much sterile water or neutral saline do we need to use? Do we need to add to the 20 milliliters of blood? Well, we have the 1 in 5 dilution, but remember the 1 there stands for the serum, in this case the blood. The 5 is the total solution. We don't want total solution, we want the amount of saline. So we're going to go for the serum, or the blood, to saline, which is going to give us a ratio of, well, still 1 part for the blood. How many parts for the saline? Really talkative group. I suppose you guys are all on mute. 5 minus 1 gives us 4 parts of saline. So now we're going to plug in, we have 20 milliliters of blood. We cross multiply and divide. 4 times 20 divided by 1. We're going to have 80 milliliters of saline added into that. Now I'm going to stress this right here because one of the biggest mistakes made in medicine is seeing a 1 in 5 dilution is desired, taking 200 milliliters of blood and just multiplying by 5 and saying, okay, we're going to add 100 milliliters of saline. That's not correct. The 5 is the total solution, which includes the blood itself. So once we've added the 80 milliliters of saline, we've diluted the blood, and we go to do a test. And again, assuming we did this correctly and the saline adds nothing to the results of the test, we can take, let's say the result is 120 or 192 milligrams per deciliter. Well, that's the diluted blood. We know that the actual reading is going to be considerably higher than that. So the actual reading, we go back to that 1 in 5 dilution. Now here's the part where matching up our numbers and our proportion is a little bit trickier. Normally we would say, well, the 5 is the volume of the diluted sample and the 1 is the volume of the concentrated sample. So you'd think the 192 would go with the 5. But in this case, this is what we call an inverse relationship. In an inverse relationship, when one number goes up, the other number goes down. And in this case, if the volume of the blood increases, the concentration decreases. If you add more water to it, the percentage concentration of glucose in the blood has to go down. So that's what we're dealing with here. The 192, in other words, is the smaller of the two numbers that we're dealing with. The actual reading has to be larger than 192. Remember, our meter went up to 800 and it exceeded the meter's limit. So we know that the result has to be bigger than 192 because we know it has to be bigger than 800. So what that means is the 192 has to go with the smaller of the two numbers in our ratio. So it has to go with the 5. Or sorry, it has to go with the 1. And the 5 will represent our actual number, the larger number. So now we will cross multiply and divide. 5 times 192 divided by 1 is going to give us, what is that, 960, I believe, milligrams per deciliter. Okay, well, let's look at another example. In this example, let's say we are doing a urine test. And in the urine test, our meter is capable of going up to 1,000 units, 1,000 milligrams per deciliter. And we need to, our patient exceeds that limit. And so what we're going to do is we're going to take a 120 microliter sample, and we are going to add 600 microliters of a neutral solution to that urine. So basically what we're looking at, we are the lab tech looking at the results. We are looking at the lab person looking at the results. We're looking at the tech who took the 120 microliters and added 600 microliters of sterile water to that, and gets a result of 203 milligrams per deciliter. We need to interpret that result. Well, the first step in interpreting what that actual result should be is to find the dilution. Remember, the dilution is, once again, the amount of serum, in this case the urine, to total solution. Well, in this case, we do have the amount of urine is 120 microliters. We need the total solution now. Well, the total solution is not the 600 microliters. The 600 was the amount of neutral solution or water that was added to it. Total solution is going to be the 600 plus the 120. So that means we have an actual dilution of 120 to 720. The microliters divide out. 120 and 720 are both divisible by 120 to give us a 1 in 6 dilution. So now that 1 in 6 is what we're going to use to figure out the actual level in that sample. So we have a 1 in 6 dilution. The 203 is the reading we got. We need to figure out, does that go on top or bottom? Where is it going to go? Well, since that has to represent the smaller of the two numbers, that's the diluted amount, and the real amount has to be larger than that, it goes with the 1. And then, of course, to find the actual reading, we're going to cross multiply and divide. 6 times 203 divided by 1 is 1,218 milligrams per deciliter. I want you guys to try one quick and see what you come up with. So again, let's say our meter, go back to blood glucose here, has a limit of 800 milligrams per deciliter. And the sample exceeds the limit. So the person doing the test combines 150 microliters of blood with 525 microliters of sterile water. The reading is 280 milligrams per deciliter. So go ahead and tell me, what is the actual result? I'll pause this for a second. Okay, let's take a look. So the first thing we have to do here is we have to figure out what dilution was used. And again, we need to know serum, in this case blood again, to total solution. Well, our serum was 150 microliters. The 525 is just the amount of the water used, so the total is the 525 plus the 150. So this becomes, I'm just going to assume that the microliters divide out again. I'm just going to skip that. So this is going to become 150 over 675. And then we're going to reduce. Let's see. Both of those can be divided by 25. I know they can both be divided by 75 too, can't they? I bet. So we get 6 over 27. Yeah, they can both be divided by 3. Give me 2 and 9. So that is a 2 and 9 dilution. So now that we have a 2 and 9 dilution, we can find the actual value. The 280 is the diluted value, is going to go on top. 280 milligrams per deciliter. And we're going to cross multiply. 9 times 280 divided by 2 is 1,260 milligrams per deciliter. Just a little show of hands. How many of you got that? Cool. Good. Anybody feeling totally lost on what's going on there? Oh, that's good at least. Let's do one more example, and then we'll be closing in on time to give you some homework for the day. In this example, we're going to go back similar to the first example. We're going to do a urine test. In a urine test, this meter is going to have a limit of 1,200 milligrams per deciliter. The sample exceeded it, of course. So we're going to look at, we have an 80 milligram sample. We are going to undergo a 2 in 7 dilution to dilute the sample. And the test result, after going through that dilution, is 390 milligrams per deciliter. So I want you to find two things. One, how much of our neutral solution did we need to use? And two, the actual reading. I'll give you a couple minutes again and we will. Okay, so our first step, finding the amount of NS. Well, this being a 2 in 7 dilution, that is, of course, in this case, urine to total. Trying to find the NS, we want urine to the neutral solution, which would be 2, still 2 parts of urine, but 7 minus 2 gives us 5 parts of water. So for an 80 milligram specimen, cross multiply and divide, 5 times 80 divided by 2 is going to give us 200, or not milligram, milliliter I should say, 200 milliliters of NS to mix with it. So once we've properly diluted it, we have 2 in 7 is our dilution still. We have a 390 reading. So the 390 goes on top. And we'll cross multiply and divide. 7 times 390 divided by 2. Gives us 1365. So 1365 milligrams per deciliter. So just a quick review. In a 1 in 8 dilution, what is the ratio of serum to saline. Give you a second to think about that. Most people's gut reaction is to put 1 in 8. But remember, the 1 in 8, the dilution, is the serum to total. We want serum to saline. Serum to NS, if you want to leave it as that. Serum is still 1 part. The saline, however, is 8 minus 1, or 7 parts. In a 3 in 11 dilution, of insulin in water, what is the ratio of water to total volume? So again, the only ratio given in the problem is the 3 to 11 dilution. But the 3 is the serum, in this case the insulin, and the 11 is the total. Now in this case, we want total in our ratio, but we want water, not insulin. So we want water to total. So now in this case, it's the 11 that doesn't change. The total doesn't change. The water, however, if there's 3 parts of insulin, there's 11 minus 3, or 8 parts of water. So in a 4 in 15 dilution of urine in water, how much of each is required for 480 milliliters of the dilution? So we have 2 calculations to make here. We have the urine, the amount of urine needed. Well, the amount of urine, the ratio there is just the dilution, 4 in 15. The 4 represents the urine, and the 15 represents the total. So we can just put in the 480 milliliters is the total, cross multiply and divide. 4 times 480 divided, oops, something wrong here. Try that again. 4 times 480 divided by 15 is 128 milliliters. So 128 milliliters of urine. Now again, we could just subtract there, but I like to double check. If we want, now we want to look at the ratio of water to total. Total is still 15 parts. The water would be 15 minus 4, or 11 parts. Still 480 milliliters, representing the total volume. We cross multiply and divide. 11 times 480 divided by 15 gives us 352 milliliters. The reason I like to set it up this way is now I can go back and I can double check my calculation. If I did these 2 ratios correctly, and if I cross multiplied and divided correctly, these 2 numbers, the 328 or the 128 and the 352, should add up to my total solution of 480, and they do. So that's just another way of double checking your calculations. With that, we have about 5 minutes left. So I'm going to give you your homework in the textbook. on page 130 through 132. Questions 1 through 37, study work on the odds. Cover dilutions and the calculations involved with dilution. Like I said, I'm going to try to have your tests graded by Wednesday. I've got to dig through my email and make sure all of them are in. If not, I'll send out messages to your coordinator at your location and make sure I have them all in. So you should have them back by Wednesday. You guys have a good day.